It's my pleasure to introduce Addison today, a graduate teaching assistant at Florida Atlantic University, my classmate and my friend, with a keen interest in mathematics and algorithms. So today she will be presenting on the stable marriage model, a fascinating topic with a real-world application in matching problems like school admissions, hospitals and patients matching, and job placement, and so many more. Okay, so please join me in welcoming Addison today.
Thank you. All right, let me go ahead and share my screen. Okay, perfect. So yeah, thank you for the introduction. So I'll be talking about the stable marriage or stable matching problem, and then the Gale-Shapley algorithm, which is used to solve it. So this is a just outline of my talk. I'll give an introduction. I'll talk about the theorem and then give the pseudocode, and then I'll give some examples of code I wrote up in Python. I'll talk about the time complexity and then take questions after that. So just an introduction as to what the problem is. So if we have a situation where we have in men and in women who are looking to get married, so we want to match them together, but they each have a list of preferences as to who they would like to marry. So they make a list of like they want to marry this one more than this one, and all the way down to including all in men or women. And then we want to figure out how we can match everyone so that they have a stable marriage. And so let me define what I mean by stable, and we'll do that by defining what we mean by unstable. So a marriage will be called unstable if we have two sets, so an alpha and an A, and a beta and a B, where alpha prefers B and beta prefers A. So we have two matches where the one of the spouse in each one prefers the other spouse in the other one. So for example, if we marry Alice and Andrew, but Alice prefers Brian, and Brian is married to Betty, but Brian prefers Alice. So you have these two marriages, Alice and Andrew, Betty and Brian, but Alice and Brian prefer each other to their own spouse, then these would be unstable because they each prefer someone else to their own spouse. So our marriages would be stable even even if one of our spouses doesn't get their top pick, the person they're married to doesn't prefer someone else who prefers their spouse. And we'll go through some examples to see how this works. And then just some other specifications. The preference list that we have, there's going to be no ties. So it's just 1, 2, 3, 4. They list it in order that they like them. There's no like ties if they like Alice and Betty the same. It's all listed in order. Okay, so we have the Gale-Shapley theorem, which proves that there always exists a stable set of marriages. So if we have just any random pattern of preferences for these in men and women, is it actually possible to marry everyone into stable marriages? And this theorem presents a proof by solving the problem with an iterative approach. So this is the Gale-Shapley algorithm. So how it works is we have our in men and women, and they each have their preferences. So we start off with each man going to the woman they like the most on their list, and they propose to that woman. It doesn't matter if some men have the same woman on the top of their list. They could all be the same woman. They each go to that woman and they propose to her. Now, each time a woman gets proposed to, she rejects everyone except her favorite one. So the one who's at the highest on their list, that's the one that she becomes engaged with. So then all of the men who are accepted become engaged. And then round two, we now each man who's not engaged goes and proposes to the next woman on their list. So they got rejected by the first one. Now they go to the next one and they see if they get accepted this time. So if the woman was already engaged, she now gets to choose if she wants her previous engagement, her new engagement, and she always picks the one who's highest on her list. So if the new person who proposed to her, if she likes him better, they'll become engaged, and then the person she was engaged to would become unengaged. And we would just keep repeating this process. The men would go to their next highest ranked women, propose to them, they become engaged, And then we do this until all the men are engaged. Okay, so let's give some pseudocode for how this works. Maybe see it a little better.
Yeah.
So the input and the way that I coded it up in Python, we're going to have a matrix of the preferences. So each, the first n arrays will be the men's preferences, and then the next n arrays will be the women's preferences. It's just how I put it in order. And then we're going to output the matching pairs of men and women. So while we have a man who is not engaged, that man, M, is going to propose to the next highest ranked woman, W, who he hasn't proposed to yet. He never goes back and proposes to someone else. Once he's been rejected, he doesn't go back. So he just keeps going down his list. So if that woman is free, if she's not engaged, then they just become engaged automatically. But if she is already engaged to another man, M prime, then we have to see who she prefers. So if W prefers M to M prime, then they become engaged, but now M prime is free. He's unengaged now. Otherwise, she stays engaged to M prime, and then M now has to go back and propose to the next highest ranked woman on his list. And you keep doing this until there's no men who are free. All of the men will be engaged. All right, so I wanted to give a little example just to kind of see how this works. So we're going to just look at a set of 3 men and 3 women. So we have Adam, Barry, and Chris, and then Alice, Bailey, and Caitlin. And this is their list of preferences. And I just used the first initial to make it easy. So Adam prefers Alice, then Bailey, then Caitlin. Barry prefers Bailey, then Alice, and Caitlin. And Chris prefers Alice, then Bailey, then Caitlin. And notice that it's okay if we have people who have the same list of preferences. It doesn't matter. We'll still get a stable marriage. And unfortunately, in this situation, none of the men really like Caitlin, but everyone will still be matched in a stable marriage. So, working through the algorithm, the first round, we start with Adam, and he's going to propose to Alice because that's the first person on his list. No one's proposed to her before, so they become engaged. Then Barry, we look back at our list, Barry prefers Bailey, so he'll propose to Bailey. No one has proposed to her, so they become engaged. Then Chris, he prefers Alice, so he's going to propose to her, but she prefers Adam. That's actually her highest pick. So she rejects Chris, and Chris is unengaged. So now we go to round 2. So Chris is the only unengaged one, so he's going to go to the next person on his list, which is Bailey. So he proposes to Bailey. Remember, Bailey was proposed to Barry. Now Chris is proposing to her, and she actually prefers Chris. So she's going to become engaged to Chris, and now Barry is unengaged. So we go back, and now Barry is the only unengaged one. He proposes to Alice, but she still prefers Adam. That's her highest pick, so she rejects Barry. So now Barry is still unengaged. So finally, Barry proposes to the last one on his list, which is Caitlin, and then they become engaged. So here are our pairs. Alice and Adam are married. Bailey and Chris are married, and then Caitlin and Barry are married. I mean, you can see that this is going to actually be a stable marriage. So if we look at our pairs, Alice and Adam, they actually got their highest pick. So their marriage is really stable. Bailey is engaged to Chris. So Chris is Bailey's highest pick. So she's not going to leave him. Chris prefers Alice, but Alice is already with her highest pick. So she's not going to leave for Chris. And then that's Bailey is his second pick. So then that marriage is stable. Caitlin prefers Barry. She got her highest pick. Now Barry prefers both Bailey and Alice, but they're already matched with someone higher on their list than Barry is. So these are all stable marriages. Okay, so I want to show the Python code really quick. Will it share? I think I need to share a new screen. Okay, are we able to see the Python code?
Yes, perfect.
Okay, so here is my Python code, this is based on the pseudocode. So let me start with just the main stable marriage code here. So we start off with creating a list of the men. They're going to initialize to be true, which means they're unengaged, they're free. And then we'll have our women's pairs. So this will be a list of the man that the woman is paired with. So the woman is the index, and then what is in that index will be who she's paired with. So if you put a 2 at index 0, it'll mean woman 0 is paired with man number 2. Okay, and then here's our main loop. So while we have a true and free man, so while there's a man who's unengaged, then we go through his list of women and we see who he prefers next. And then so then we find the next woman in his list, that'll be W, and then we see who she's already paired with. So that'll be M prime. So if M prime is -1, that means she hasn't been engaged to yet. So then she just becomes engaged to that man M because she's not engaged yet. Otherwise, if she has already been engaged, then we look to see who she prefers. So that's the prefer M to M prime. So that's this code up here. All this does is it goes through her list of preferences, and whichever man we come across first would be the one she prefers. So if we come across M first, she prefers M. If we come across M prime first, then she prefers M prime. So we look at, see who she prefers. If she prefers M, she becomes engaged to him, and then he is now unengaged. Or sorry, he is engaged, so he's no longer free. So we change that to false. And then now the M prime has to be switched to true because now he's unengaged. So then we just keep going through all of the list until all of our men are engaged. And then we'll print out everything here. So here's the code I wrote up for the example I went through. So in this case, since I had to label them with numbers, A is 0, B is 1, C is 2. So this is like Alice, Bailey, and Caitlin. And if we just run this, these will be our matches. So this is Alice and Adam got matched. Bailey got matched to Chris, and Caitlin got matched to Barry, which is what we had when we worked through it step by step. Okay, and then I did a couple different preference lists. This is another one of preference 3, just to see that we can come up with different matches, right? So this is 0 is matched to the first one, 1 is now 0, and 2 is a 2. And we can do it with longer lists too. I'm just going to show an example down here of this one. So this is one where I did a list of 10 men and 10 women. So these are all our preferences. So the first 10 are the men's preferences, and I just generated random permutations. And the second 10 are the preferences for the women. And just to see that we can still get a stable marriage quickly here, these are what we have matched here. Okay, so let me go back now and talk about the time complexity. Okay, are we able to see the PowerPoint?
Yeah.
Okay, so this algorithm actually, we have proved that the stability is actually guaranteed. So this is the proof that Gale and Shapley presented in their paper when they presented this algorithm. So they suppose that John and Mary are not married to each other, but John prefers Mary to his own wife. So either John proposed to Mary at some stage and was rejected in favor of someone that Mary liked better, or okay, so that means if John prefers Mary to his own wife, then he must have proposed to her previously, but she rejected him for someone she likes better. So she must prefer her own husband to John. There's no way that if we followed this algorithm, that Mary would actually prefer John to her own husband, because if she did, she would have picked John when he proposed to her. And since our men, they always propose to every woman until they become engaged, he would have had to propose to her at some point if he liked her better than his own wife. So stability here is just guaranteed by how we constructed the algorithm. All right, so we want to talk about time complexity and why this is a nice algorithm. So the naive approach, if we just had these in men and in women, and we just wanted to try to create some stable marriages, would just be to kind of guess. And the worst case scenario of getting stability is if we somehow do a really bad job of picking them, and each time we just make a list, we match the in people, and then we check it and it's wrong, and we do it in factorial times, right? You just, each time you guess, you have to check it's wrong, you just keep going through each possibility. So this would be in factorial, would be the worst case scenario if we just took a naive approach. But the Gale-Shapley algorithm is actually big O of n squared. So at most, n squared minus n plus 1 proposals are required. So the worst case scenario in this algorithm is if every woman except the last woman receive n proposals, and then the last woman receives one. So if everyone just really dislikes one woman and they keep proposing to all the other women, and then each woman would keep their favorite. So you would start out with n, and then n minus 1, and then n minus 2. You'd have to go all the way down until the last woman receives her proposal. This would be the worst case scenario. And then this would be n times n minus 1 plus 1 would be how many iterations we would have to do. But this would just be worst case scenario. But even then, this is still much better than n factorial. So this algorithm is really nice for these types of problems. And this problem, I picked the stable marriage application because I thought it was more fun to go through, but you can apply it to different situations like matching doctors to hospitals is one of the big ones that they've used, and also matching students to colleges. So students applying to different colleges and colleges accepting different students. They can accept more than one student. It doesn't have to be just matching one to one like in the marriage situation. You can change it so that you can match like multiple students to one college. But either way, we can still apply the same algorithm, and it would still be of smaller time complexity than just the naive approach. And that's all. Thank you.
If the stable marriage model, can handle math making for marriage, it must be a pro for at handling college admissions, right? So how does it ensure fairness and stability in that context in the college admission context?
It's the same algorithm. So you would have, go back to here. It would be the same thing, except instead of men and women, you would have colleges and applicants. And then you would just have to edit it so that there's a limit to like how many students a college accepts. So like if they wanted only accept 2 students, then they would have to limit that. But it would be the same process where each student would apply to, I think, all the colleges that they like, and then the colleges would just always pick their favorites. So if they only wanted to accept like 3 students, they would just pick like their 3 favorites, right? And then the students would just be left with the ones that they liked, but then only in order that they on their list of preferences, if that makes sense. So it would still be the same thing where they just become engaged, and then the school, like the women, just picks their favorite each time.
Thank you. Pitamar, do you have any question?
Yeah, the wonderful presentation. So thank you for your presentation. So How do you rank the men or women? So there are, for example, you have M proposes to highest ranked woman. So how can we calculate the highest rank woman? It is
This is
based on the feelings or emotions.
Yeah, I mean in this in this situation it's just their feelings of what they like most, right? It's just their list of preferences.
Hmm.
And but we had to they just make sure they're not like tied. So in this case, like Adam, like he likes Alice more than Bailey. It's not like he likes them the same, so that we always make sure we can just go down that list and they're each at a different ranking. But yeah, it's really just feelings for them, what their actual preferences are.
Maybe in case of accepting the applicant in college, there could be the highest rank student that college wants
Yeah,
to admit, right? And the likewise that happens maybe in the hospital and doctor,
yeah, it
maybe
happens because we
yeah,
have the university ranking are common. So
yeah.
student
Mhm.
rank the university, that's okay. But based on
Yeah.
human feelings, yeah, it is just the preferences, I hope.
Maybe
Yeah,
there
I
is some
think
kind of
so.
maybe there would be some kind of research like I don't know if that can score for a man and woman in the psychological perspective. They could make a score on that. I don't know. Maybe that.
Maybe that's true.
All right. Yeah. Thank you very much.
All right,
Thank
thank
you,
you.
Addison.
All right.